Hello everyone, I am Charles. In this video, I will present our paper, Autoscaling High-Throughput Workloads on Container-Orchestrator. Here is an outline of the presentation. First, I will introduce the problem we try to solve, which is directly running high-throughput computing workloads on Container-Orchestrator can cause low resource efficiency and long workload execution time. Second, I will give our solution to this problem, which is a feedback autoscaling mechanism that considering workload attributes as well as the platform status. Based on this mechanism, we develop an high-throughput autoscaler. At the end, I will give some evaluation results. We compare our high-throughput autoscaler with the Kubernetes default autoscaler, horizontal pod autoscaler, by considering two kinds of workload, a CPU-bound workload and an I/O-bound workload. Next, let me explain the problem we try to solve. What is high-throughput computing workload? What are some unique characteristics of the high-throughput computing workload compared to other workloads? High-throughput computing workloads seek to complete as many jobs as possible over a long period of time. The users of the high-throughput computing workload care more about how many jobs can be completed during a long period of time, rather than how fast a single job can be completed. Therefore, it is quite common that the high-throughput computing workload use up all the available resource assigned to them, and the full resource utilization is the normal state of an high-throughput computing facility. In some extreme cases, the high-throughput computing facilities have to run multiple workloads concurrently, which may cause some of the workloads cannot scale up to the desired degree due to the lack of resources. On the other hand, public cloud providers like Amazon Web Server and the Google Cloud Platform render rapidly evolving hardwares, almost infinite computing resource, and the state-of-the-art system and software. Therefore, migrating high-throughput computing workloads to the public cloud provider may be a solution to the shortage of local resource. However, the resource management system used by the public cloud provider, like Kubernetes, are usually designed for latency-sensitive servers, like web server, streaming, or gaming applications. Short response time is critical to these applications. If the resource utilization is too high, the response time will go up and the latency will be prolonged. At the same time, most cloud providers stick to the pay-as-you-go budget rule. Therefore, autoscaling the resource pool based on the service response time or resource utilization is the key functionality that need to be rendered by the public cloud platform. A standard way of running a latency-sensitive service on a public cloud platform is user choose a system metric as an indicator, like CPU, memory, or disk utilization. Then set a threshold value for this metric, like the CPU utilization cannot over 50%, and provide the budget limit, like the maximum amount of CPU can be created. Then the cloud manager will autoscale the resource pool based on this system information during the runtime. But high-throughput computing workload doesn't care about the response time, and the full resource utilization is the normal state. It is difficult for the users of the high-throughput computing workload to specify an indicator and a threshold value. If the threshold value is too low, the resource pool will keep scale up, which can lead to low resource utilization in the end. If the threshold value is too high, the resource pool will never scale up, which will lead to long workload execution time. Therefore, direct running high-throughput computing workload on this system can cause low resource efficiency or unacceptable performance. Next, I will introduce our solution to this problem. Before talking about the solution, let me introduce how to run high-throughput computing workload on a cluster. Running high-throughput computing workload on a cluster usually involve three components. They are the workflow manager, the task scheduler, and the cluster manager. The workflow manager is the software that allows user to describe the workflow structure. After user describes the workflow structure, the workflow manager will analyze the structure and submit the task to task scheduler. Task scheduler is the framework that deploys worker process across available computing resource, receive task from workflow manager, and assign task to proper worker process. Cluster manager is the software that abstract computing resource from physical hardwares and provide a view to the upper layer user or application that they are going to use resource from an unified resource pool instead of independent different physical machines. In our case, we are going to use Makeflow as the workflow manager, WorkQ as the task scheduler, and Kubernetes as the cluster manager. Previous studies have suggested various mechanisms of managing computing resource for the workload. Depending on which component is mostly responsible for managing the resource, they can be divided into three categories. First, we can reserve the resource in advance. This can be done by using the workflow manager, by analyzing the workflow structure and use the historic data as the reference. The workflow manager can roughly estimate the resource request of the workflow and reserve resource in advance. The drawback of this mechanism is obvious. If we migrate the workload to a new environment with different system setup, then historic data will be useless. The second option is resizing a resource pool based on the task queue status. However, provisioning resource takes time. It is quite common that when a newly created resource are ready, the waiting tasks have already finished. Another option is relying on the system matrix of the cluster manager. But as we mentioned before, this mechanism is good for latency-sensitive servers, but not for high-throughput computing workload. We believe that a good autoscaling mechanism for high-throughput computing workload should collect information from all these three components. So, how does the resource relationship look like during the lifetime of a workload? As we can see in the figure, the solid line represents the resource demand of the workload. The dashed line represents the resource supply of the cluster manager. The shadow area represents the resource shortage, and the dark areas represents the resource waste. Our objective is to minimize the resource shortage and the resource waste. To achieve this, we have to get three pieces of information. First, the resource initialization time of the cluster manager. Because every time when we proceed in the resource estimation, we wanted to foresee the resource relationship of a future time point. Therefore, we want to make sure when the newly created resource are ready, there is no resource waste or shortage. Second, the workload runtime status, like how many tasks are waiting and how many tasks are running. Third, the task level information, like resource request and the execution time of each single task. By combining these three pieces of information, we will be able to know how many resources are required at a time point when a newly created resource are ready. More details of the algorithm can be found in the full paper. We can get the workload runtime status by querying the task scheduler. But how can we get the task runtime information and the resource initialization time of the cluster manager? We can leverage two insights. The first insight is related to the high-throughput computing workload. High-throughput computing workloads often consist of multiple stages, and the parallel jobs from the same stages are usually copies of the same program that have similar size of input and output data. Therefore, if we can know the resource consumption and execution time of one task, we can apply this information to all tasks from the same stage. The second insight is related to the resource provisioning mechanism of the Cloud Manager. Cloud Manager usually processes resource reservation requests in batch, and we guess the resource request from same batch that asks for the same machine type in the same geographic region have similar resource initialization time. To verify our guess, we benchmark the pod initialization time on GKE by creating 10 pods from the scratch simultaneously. The pod creation includes reserving the new computing node, and pooling the container image. As we can see, the average pod initialization time is around 150 seconds, but the standard deviation is only 4.2 seconds. Therefore, we can conclude that the initialization time of the same resource type are similar, and the resource pool size is constant when the newly created resources are under provisioning. Before we introducing the implementation details, we need to figure out one more thing. When running a high-throughput workload with our system set up, there are 4 abstractions involved. They are task of workload, worker of the task scheduler, Kubernetes pod, computing node of the cluster manager. We have to figure out how to align these 4 abstractions. First, for high-throughput workload, it is very common that tasks from the same stage share the same chunk of input data. In order to reduce the data transfer and the network overhead, we decide to run multiple tasks per worker. Second, we want to simplify the implementation and achieve the cascading deletion and creation. That is to say, we want to resize the resource pool by deleting or creating one of the abstraction. To this end, we run 1 worker per pod and 1 pod per node. Next, let's talk about how to collect the task level information. We are going to use a module of the Makeflow called Resource Monitor. Resource Monitor helps us to collect the task runtime information by first, use a complete worker to run the first task of each stage, since we doesn't know the task resource request yet. Second, once the first task successfully complete, the Resource Monitor collect the task runtime information like the max resource request and the task execution time, and report it back to the Makeflow. Third, we can apply this information to tasks from the same stage and run multiple tasks inside 1 worker, and also use this information to estimate the resource request of the workload. In addition to the task level information, we have to collect 2 pieces of runtime information, which are task queue status and the resource initialization time. As we mentioned before, task queue status can be got by querying a work queue. For the resource initialization time, we are going to use the Kubernetes Informer library. The Informer library allows users to register callback functions for specified resource. Once the resource status is updated, the user will get noticed. In order to get the resource initialization time, we register a callback function with the pod resource type. On the left-hand side, we show the complete life cycle of a pod. Assume that we create a new pod and there is no available resource. Then we will start at the upper left state, no available node. The pod phase will be pending, and the pod event will be insufficient resource. After a while, the cloud manager will add a new node to the cluster. The pod phase will still be pending, but the event will be updated to pooling image. After the image is pooled, the pod phase will become running, and the pod event will be updated to container started. By recording the timestamp of these 3 states and subtracting the timestamp of the third and the first state, we can get the resource initialization time. And we will keep update the resource initialization time throughout the lifetime of the workload. So far, we have collected all the required information, the resource initialization time, the task queue status, and the task level information. Then we develop a feedback autoscaler called the High-Throughput Autoscaler that divides the workload lifetime into time intervals, with each time interval equals to the latest resource initialization time. Then estimate the resource shortage at the end of each time interval, and scale the resource pool based on the estimated result. Next, I will compare our high-throughput autoscaler with the Kubernetes default autoscaler, that is, the horizontal pod autoscaler, and give some evaluation results. Specifically, we consider 2 workloads, a CPU-bound workload and an I/O-bound workload. We run each workload with 3 system configurations. They are horizontal pod autoscaler with 20% of CPU usage as the threshold value, Horizontal-Pod Autoscaler with 50% of CPU usage as the threshold value, and High-Throughput Autoscaler. All experiments are running on a GKE cluster with Kubernetes version 1.13. The cluster can be scaled up to 20 nodes, with each node has 4 virtual CPU, 15 GB of RAM, and 100 GB of disk space. To avoid network speed variation between a public container registry and the daemon, we set up a private container registry on the Google Cloud. First, let's take a look at the CPU-bound workload. We use the BLAST bioinformatics workload as the CPU-bound workload, which consists of 3 stages. As we can see in the upper right graph, the first and the last stage of the workload contains tasks more than the second stage. An optimal autoscaler should resize the resource pool follow the same pattern. That is, shrinking the resource pool at the second stage and increase the resource pool at the third stage. On the left-hand side, we show the resource relationship of the 3 configurations. The x-axis is the time. The y-axis is the number of cores. The red line represents the resource demand, and the green line represents the resource supply. As we can see, regardless what CPU load we set, if we use the horizontal pod autoscaler, we will fail to scale down the cluster at the second stage. This is because, to avoid the pods from thrashing, there is an interval between 2 scale operations, during which the pool size will not be changed. Even though we can change the length of the interval, different workloads have various resource changing rate. Without running the same workload multiple times, we can't decide the right value. In contrast, High-Throughput Autoscaler resizes the cluster as expected, which reduces the resource waste by up to 5.6 times. CPU load is usually a good indicator, but application's performance can be bound by other kind of resource. If the user chooses the wrong resource as an indicator, the resource pool will never be scaled up. Let's take a look at an I/O-bound workload. We create a synthetic workload that contains 200 I/O-intensive tasks. In the left-hand side, we show the resource usage of the 3 configurations. We consider the same dimensions as the previous experiment. As we can see, if we choose to use horizontal pod autoscaler, no matter what CPU load we set, the cluster will never scale up. This is because all task is busy at reading or writing data, and the CPU load is never over 20%. In contrast, High-Throughput Autoscaler does not require the user to choose an indicator or a threshold value. It considers the workload attribute as well as the platform status and scale the resource pool on demand. Compared to the HPA, High-Throughput Autoscaler shortens the workload execution time by up to 3.6 times. To conclude, in this paper, we developed a feedback autoscaling mechanism for running high-throughput workload on Container-Orchestrators, which estimate the resource shortage based on the task-level information, workload runtime status, and the platform status. Based on this mechanism, we developed the High-Throughput Autoscaler. Compared to the default autoscaler of Kubernetes, the High-Throughput Autoscaler improved the resource usage of the CPU-bound workload by 5.6 times, and shortened the workload execution time of the I/O-bound workload by 3.6 times. Okay, that's all for this video. Thanks for watching. If you have any question, you can find me at this email address. Feel free to read the paper and try out our softwares.